Hello students, I am Snehal Mure. Welcome back. This is our third virtual e-learning session on wave optics. Before we start today's session, let us have a quick recap of previous session. We discussed Huygens theory, sources of light, wavefront, types of wavefront, Huygens principle, and progress of a plane wavefront. In this session, we will cover progress of a spherical wavefront and reflection of light at a plane surface. Let us discuss progress of a spherical wavefront. If we know the shape of a wavefront at any time, we can easily determine the shape of a wavefront at any later time by means of geometrical construction based on Huygens principle. A spherical wavefront is formed when the point source of light is at a finite distance from point of observation. Let S be the point source of light. AB represents a spherical wavefront at time t equal to 0. The wavefront AB acts as a primary wavefront. Look at the figure. According to Huygens principle, all the points on AB act as secondary source of light and emit secondary wavelets with same speed v in forward direction. As discussed earlier, backward traveling wavelets are supposed to be ineffective. Draw hemispheres with P, Q, R as centers and Vt as radius, where v is speed of light in the medium and t is the time. So the distance covered by the secondary wavelets will be Vt in time t. Draw a tangential surface to all these hemispheres. The surface tangential to all these hemispheres represents the wavefront at time t. So the wavefront at time t will be the envelope of all these hemispherical wavelets and will be a spherical surface A', B'. Such a surface is passing through all points such as P1, Q1, R1 on the hemispheres and touching all the hemispheres. The new wavefront A', B' is a spherical wavefront at time t equal to t. The new wavefront A', B' is parallel to AB. SPN1, SQN2, SRN3 show the direction of propagation of the spherical wavefront. A', B' represents a new spherical wavefront at time t equal to t. Reflection of light at a plane surface. We shall now see how Huygens succeeded in explaining the phenomena of reflection of light. Let us discuss reflection of light at a plane surface. Look at the figure. Mn is a plane reflecting surface. AB is a plane wavefront. EC is the reflected wavefront. AP is the normal to Mn at point A. Angle RAP is equal to I, angle of incidence. Angle PAE is equal to R, angle of reflection. Consider a plane wavefront AB which is perpendicular to the plane of the paper. It is incident obliquely at an angle I with the normal to a plane reflecting surface MN, which is also perpendicular to the plane of the paper. AB is a plane wavefront. It is perpendicular to the plane of the paper. It is incident obliquely at an angle I with the normal to a plane reflecting surface MN, which is also perpendicular to the plane of the paper. RA and QB are incident rays. Let us assume that AB touches the reflecting surface at A at time t equal to 0. Initially, only A touches the reflecting surface. Point B will take some time to reach C. As the wavefront is obliquely incident, the point B will touch the reflecting surface at C after time t equal to t. According to Huygens' principle, as soon as the wavefront reaches A, it becomes a secondary source and starts emitting secondary wavelets in the form of hemispheres. At time t equal to 0, wavefront reaches at A, and at time t equal to t, it reaches at C. So between time t equal to 0 to t equal to t, different points along the incident wavefront reach the reflecting surface successively and start emitting secondary wavelets in the form of hemispheres. Initially, the incident wavefront reaches at A and it starts emitting secondary wavelets. Then, one by one, points will reach the reflecting surface and start emitting secondary wavelets. And at last, B reaches at C. As the incident wavefront from B takes time t to reach C, the distance covered by the incident wavefront is BC, that is Vt, where v is the speed of light. During same time t, the secondary wavelets from A will cover the same distance Vt in the same medium. To find the position of the secondary wavelets emitted from A after time t, draw an arc with radius Vt and center as A. The radius of wavelet emitted by A at time t is Vt and the radius of wavelet emitted by C is 0. If you observe the figure carefully, you will notice that the radii of wavelets between points A and C will gradually decrease from Vt to 0. At A, radius is Vt. Then it goes on decreasing and at C it becomes 0. Now, if we draw the hemispheres with these radii, Then the surface touching all these hemispheres is EC, which is the reflected wavefront. The reflected wavefront is the envelope of all these secondary wavelets. EC is the common tangent to all these reflected wavelets between points A and C. AE and CF are reflected rays. Look at the figure carefully. BC is equal to VT. AE is equal to VT. Distance travelled by light in the same time in the same medium. AE is equal to BC is equal to VT. The arrow AE show the direction of propagation of reflected wave. AP is normal to MN at A. Angle RAP is equal to I, that is angle of incidence, as RA is perpendicular to AB, AP is perpendicular to AC. Therefore, angle BAC is equal to I. Angle PAE is equal to R, that is angle of reflection. Triangle ABC and triangle AEC are right angled triangles. AC is the common hypotenuse. AE is equal to BC. Triangle ABC is congruent to triangle AEC. Angle ACE is equal to angle BAC is equal to I. AE is perpendicular to CE. AP is perpendicular to AC. Angle ACE is equal to angle PAE is equal to R. From equation 1 and 2 we get I equal to R. Angle of incidence is equal to angle of reflection. It is also clear from the figure that incident ray, normal and reflected ray are in the same plane. Laws of reflection are proved on the basis of Huygens wave theory of light. AB is size of the object. The distance between the corresponding reflected rays AE and CF is same as AB because triangle ABC and triangle AEC are congruent triangles. The size of the object in the reflected image is same as the actual size of the object. Okay, Now it's time that we test our understanding of what we have covered so far and apply that to the next set of questions. So we have very easy questions at our hand. It is a MCQ. The wavefront originating from the point source of light at a finite distance is a. You are given four options. You have to select the correct one. The wavefront originating from the point source of light at a finite distance is a spherical wavefront. The next one, Huygens concept of secondary waves. You are given four options. Select the correct one. Huygens concept of secondary waves is a geometrical method to find a wavefront. Until next time, happy learning.